I think we are talking about the nomenclature last time, right? Do you have any question on that? If you have the molecule, something like this, you can name that, right? Oh, yes.
Can we run through it just real quick?
Alright, so here you have two functional groups.
Yes.
So you have alkene and alkyne, right? So both gonna have the same priority if you compare with the other one, like alcohol, carboxylic acid, other functional groups, right? But when you have both in the molecule, you're gonna do the alkene first and then the alkyne later. Okay? So that's why you're gonna put En before Yn. Alright, so always do that. So whenever you're gonna have the lowest label on the carbon, doesn't matter alkene or alkyne, because both gonna have the same priority. For numbering, you're gonna choose the closest one, doesn't matter which one. Okay? So you're gonna number on that and then just write the position of alkene first and then position of alkyne after that. If you have any substitute, put in front. Right? So that's it. So everything is same as before, except you're gonna write the in labeling first, followed by yn label after that. That's the difference. Okay, other than that, choosing the parent chain and then numbering it, see the substituent, and then order in sequence, right? Yep. Which one?
Can you circle the substituents that make that E?
Oh, okay. So, okay, I'm gonna review it. Okay. So, you have two options over here, right? So, which gonna be the longest chain? So, I'm gonna start from the right with the red color. 1, 2, 3, 4, 5, 6, 7, 8. So, this is 1. So, other, the same length, I can do with the green color from the left. So 1, 2, 3, 4, 5, 6, 7, 8. Okay? So parent, the longest possible is gonna be the 8 carbon. Right? So you have two ways to do that. One, you can start from the right, the red color, and then you're gonna go all the way to the left. Other, you can start with the green color. So starting from the left, you're gonna go all the way to the right. Okay? Now one is correct, other is not correct. Right? So the red is correct, green is not correct. So why? The same rule, when you label carbon atoms, the functional groups, if you have many, the priority group should be closest if you compare to the other one. Right? So here both gonna have the same priority, then doesn't matter which one, but you must have one closer if you compare to the other one. So from the red color, you have number 1 carbon that is triple bonded. Okay? If you go with the green one, you're gonna have number 3 carbon that is double bonded. Okay? So which is closer, number 1 or number 3? Number 1. That's why you're gonna choose the red color. Okay? So now you know the position, so see the substituent over there. So you have the methyl there, right? So methyl, you're gonna see the red color over there. So 3 carbon has methyl, right? So you're gonna have 3 methyl. That's the substituent. That's why you have 3 methyl over there. And then you're gonna have the parent. So you have 8 carbon, so oct gonna be the base for that. Right? And then you're gonna have the alkene and alkyne, both, right? So you're gonna write the labeling for the alkene first, and then the alkyne after that. Okay. So what is the labeling for the alkene? Number 5, right? So that's why you have the 5-ene for that. And then you have number 1 carbon triple bond, so 1 yn. And then E is, you don't have any other functional group. If you have alcohol, for example, you're gonna call the OL after that, right? But here, just you have the alkane, alkene, alkyne, so E gonna, yeah. Oh, easy, okay. So now this one, so E, so sometimes you're gonna have this twice in the answer, sometimes not. So this is the extra information, okay? So E and G are gonna be first, and now I'm gonna ask you one question. So E and G, right? Or you can say cis and trans, okay? Cis trans. So this notation applies to which of the following? Alkane, alkene, or alkyne, YNE. All are one of 3 or 2 of 3. Okay. All of, right? So you're gonna apply to all. Right? Correct me if I'm wrong. So say example alkane, right? So I have the carbon, say ethane derivative. So I'm gonna have the chlorine over here, for example. Okay. And then I'm gonna have the chlorine over here. And then I'm gonna have the hydrogen, 2 hydrogen, right? Over there. So hydrogen and hydrogen, right? Dichloroethane. That's the molecule. This is alkane derivative, right? So now, can I do cis or trans E or G for this molecule? I cannot. Okay? It does not apply to alkane derivative. So this does not. Doesn't matter what type of molecule you have. Okay? Same for alkyne. So if I write alkyne, so you're going to have the triple bond there. So let's say you have chlorine over there, a chlorine over there, right? So I cannot do that, right? So you cannot see the plane with the triple bond and then one over the other, right? So you have only 2 of them, so they are linear, so you don't have the different orientation of that. So this name does not exist there. So this is not. So now, cis trans EG is applicable only for the alkene and derivative, not other. Okay, so that's the reason why whenever you're going to write the E and G, what are you going to do? You're going to focus on the double bond. So you're going to focus on this part of the molecule over here. That's going to give either cis trans or EG, right? So if it is simple alkene with just the 2 substituent in it, you're going to call the cis and trans. If you have more than 2 or the complicated molecule with the other functional groups and other groups, you're going to call E and G. So both will do for the same thing. So E is like trans, and then G gonna be like a cis. So same behavior. So for the G, you're gonna have the different groups, more than 2. So the larger groups are gonna be on the same side, if it is G, okay? And then if it is E, like over here, the larger group is gonna be in the different side of the double bond, okay? So now, what are you gonna see? So reference is gonna be this double bond, and then now you're gonna see the larger groups. Let me circle that with the green color. So this gonna be one larger group, and then the other gonna be this one, right? So are they on the same side of the double bond or on the different side of the double bond? To be same side, what do you need to have? Like say this is the double bond, right? So to be on the same side, you're gonna have the larger group over here and the other over here. In the same side, the orientation is gonna be in the same side of the double bond, right? That's gonna be G, okay? If you have one over here and then the other one to the other side of that, if you have that, gonna be E, right? So here you have one like this, other like this, so you're gonna call E for that. Okay? So if you are confused, just remember one thing. So cis is like G. Just remember that. Right? They'll be in the same side. If you remember that, other gonna be trans and E gonna be in one group. Just remember one. Good? Alright. So now you can answer this, right? So now this is gonna be also kind of like a revision we went through before. So molecular orbital of alkyne. So if you compare with the alkane, alkene, and this, so you're gonna have the different hybridization, right? So you have the same carbon atom, you're gonna have the similar type of bonding, but you're gonna have different types of, different number of bonds, right? So let's say, just to compare, so you're gonna have the alkane, right? So you're gonna have that. So 3 hydrogen over there. And then alkene, you're gonna have 2 hydrogens there on each carbon. And then if you have the triple bond, then you're gonna have the only 1 hydrogen there, right? So here we are focusing on this. Right? So you already know alkane and alkane. So what's gonna be the bonding? So if you just write with notation, you're gonna write all sigma for alkane. So you don't have any pi bond there. All the bonds between carbon-carbon or carbon-hydrogen can be sigma, right? So now why you have all sigma? That means you do not have any pure p orbital involved in the bonding. That's the reason why. Right? So now if you focus only 1 carbon, say the right carbon over here, let me write for this. So for this, what you have initially is 2s and 2p as valence orbital, right? I'm not writing core, just the valence. N equals 2 cell, right? So 2px, 2py, 2pg, right? So how many electrons you have? 4, right? Like that. So now you're gonna mix all of them, and then you're gonna have something like this with the 4 of them with 1 electron each. So these are hybrid, right? So what kind of hybrid? How many orbitals you mix there? So you mixed 1 s orbital, and then how many p orbitals? 1, 2, 3. Right? You mixed all. So it is called sp3. 1 s orbital, which is 2s. and then 3 p orbitals, which is px, py, pz, right? So why I mixed all? I need 4 orbitals to make the bond, right? So you have total 4, so you have to mix all. That's why I mixed all that. That's P3. So that's what you're gonna see in alkane. Okay? And alkene, you're gonna modify a little bit. So first count how many sigma bonds you have. 1, 2, 3, 4, 5. And then the double bond, the second gonna be the pi. You cannot have 2 sigma bonds in the same orientation. Okay, so 1 pi. So now this is different than alkane. So now you cannot mix all 4 orbitals there. Why? If you see 1 carbon, how many sigma you need? So you're gonna need 1 sigma, 2, 3. So now you need 3 hybrid orbitals, not 4. Before you had 4 sigma bonds, so you have to have 4 hybrid orbitals to make that. Now you have only 3, not 4. So you're gonna mix only 3 orbitals to have that. Okay? So then which gonna be that? So for this carbon over here, you're going to have the same orbital as before, the valence orbital, right? 2px, 2py, 2pz. So you have 2 over here, 1, 1, right? So now, what you're going to do is you're going to mix only 3, like that. Not the 2pg. You don't mix that, right? So now, what you're gonna have is you're gonna have only 3 hybrid. So this gonna be hybrid, and then 1 gonna be with the higher energy, which is 2pg, separate. It's not mixed there. Okay. So 1, 2, 3, 4. So now you're gonna have the 3 orbital. This is sp2 because you are mixing only 1s and 2p orbitals there. The third p is not mixed. It is as is, 2pg there. Okay? So that is for alkene when you have double bond. Now here we are doing the triple bond, right? Now you're going to answer how many orbitals you're going to mix. So I'm going to have the same number of initial orbitals. So I'm going to have the 2s as before, and then I'm going to have the 2px like before, 2py like before, 2pz like before, right? Now if you see the sigma bonds, how many you have? This one, and this one. So remember, you can have only 1 sigma bond in one orientation. Okay? So now you're going to have the 2 pi bonds over there. So 2 pi. So focus on the sigma bond. So for 1 carbon, how many sigma bonds you have? 1 with hydrogen, 1 with carbon. So 2. Right? So 1 with hydrogen atom. Other sigma bond going to be with the neighboring carbon. So you have 2 sigma bonds for each carbon atoms there. Okay? So now for 2 sigma bonds, how many hybrid you need? You need 2, right? So now you're going to mix only 2 orbitals. So then what I'm going to do is I'm going to mix only these 2. Right? So we have electrons as before. So then this is going to give these two hybrid. So this is hybrid, which is sp hybrid. And then you're gonna have the pure 2p orbitals, 2py, 2pg. This is gonna be pure p orbital, not mixed. Okay? So now how you're gonna represent that? Let me write one carbon atom. So one sp orbital gonna be like that, other gonna be like that. So this is sp, this is sp. So now you're gonna have the pure p orbital, right? So one pure p orbital gonna be like this. This is 2py, and then you're gonna have the another pure p with equal low. So this gonna be 2pg. Right? So how are you gonna stay is that, say this is the end carbon you have. So hybrid gonna be like that. Another hybrid gonna be like this in one plane. And then py and pg gonna be perpendicular to this. So py gonna be like that. Half lobe gonna be above this, and then the another half gonna be below this. So perpendicular to this plane, right? And the G gonna be also perpendicular, but in the other orientation. So this is gonna be half lobe, and then this is gonna be half lobe, right? You can think like this. So if you see 3 axis coordinate, so for this carbon atom, let's say this is x-axis, right? So let's say this is y-axis, then what's going to be z-axis? Like that, 90 degree, right? So 2py going to be along y-axis. 2pg going to be along the z-axis. And then the hybrid going to be along the x-axis plane you have. Okay? So that's how we're going to have the bonding. And then this is how we're going to represent. So this going to represent 2py, one of these two. And then the other going to be 2pg. So these going to make the pi bonds you have. And then, though just the line you see over there, these are hybrid, sigma bonds. Okay? So now, this is not different than alkane-alkene, right? The only difference is you're going to have the different degree of hybridization. You're going to have the different number of pi bonds, but the orbital mixing, that's going to be the same as before, right? Now here you not only see the alkyne, but you know for all alkane-alkene molecular orbital, kind of just revision. Good? So now you are conform with sp, sp2, sp3 hybridizations on the carbon when you have sigma bond or sigma and pi bonds. Right? Good? Any question on that? All right. So now, the next thing gonna be, since you have the pi bonds for this molecule, 2 pi bonds, so one gonna be this, other gonna be this, and then the one in the middle gonna be sigma, right? Always. So this gonna be sigma. So you have 3 bonds there. So now, if you recall, alkene to alkane. So which was more stable? I'm going to write the diagram. So you had something like that. So that was alkane. And then that was alkene. So this is going to be the energy you have. So larger the energy you have going to be less stable. Lower the energy you have going to be more stable. So alkane is more stable than alkene. That's why it is called saturated hydrocarbon. Right? You can see that diagram. Alkane, remember A and E. So that's going to be at lower position than alkene. Okay? So if you take that as a reference, then what do you think? Where going to be alkyne? Above alkene or below alkene? Above, right? So going to be somewhere over here. So that's going to be alkyne. Right? So that's why it is also unsaturated. So more degree than alkene. You can have one more degree of unsaturation than alkene. So that's why if you add hydrogen on that and make alkane from there, so you're going to have that energy, right? This is going to be released. You guys doing good on the back there? Good? All right. So this is going to be the total 65 kilocalorie, going to be starting from alkyne to alkane, right? If you just separate that to alkyne to alkene, so about half of that. So this is going to be the energy you're going to have, right? So this to that going to be this much energy difference, and then from the alkane to alkene, or if we go from this to this, that's going to be the difference. So total going to be like that, right? So more negative value you have is the less energy, right? So negative value means you're going to have the position lower in the diagram. The positive going to be in the higher in the diagram. So more negative means more stable. Okay? So that's what it means. So relatively, you don't need to memorize the number there. Relatively, Y and E going to be on the top. Then you're going to have the E and E, and then you're going to have A and E on the bottom. Okay? So that's the trend. That's what you're going to remember, the relative. All right. So now, once you know that, so bond strength. So this is like a review of Zenchem. Remember you had the tables of bond energies in the Zenchem 1. So you have different bonds there, carbon-carbon, single, double, triple, carbon-nitrogen. You have the bond between different atoms, right? So here, just if you compare the relative energies within the carbon-carbon framework, single, double, triple, for example, right? So you don't need to know the number. So relatively, which one do you think going to be stronger? Triple or double or single? Triple, right? It's kind of like tied by the three ropes together. Of course, going to be stronger, right? So triple bond going to be stronger than the double bond, right? And then double going to be stronger than the single bond. So that's the obvious one. Again, you're going to go to the thermodynamics and kinetics. So we're going to compare energy difference and the EA value, and then you're going to take the sum of that. So bond length, so which going to be the longer, which going to be shorter? So don't be confused, stronger and the bond length.
The triple bond is going to be shorter.
Triple going to be shorter? Yep. It's like a spring. So stronger spring, you're going to compress more further, going to be closer, right? Going to be harder to stretch that. But the weaker, going to be longer, right? So in the same way, you can say that the triple going to be shorter, double going to be in the intermediate, single going to be the longer one, right? So you can say single longest, triple shortest. And the double gonna be in between, right? So those orbitals, now you know that, sp, sp2, sp3, right? So you don't have any problem on that. But the S character, okay. So do you have any confusion on this? When you have the hybridized orbitals, you can identify the percentage of S character there, right? So you have sp, sp2, sp3, sp2, sp3. Just count how many orbitals you have in the mixed form. So for sp, you have the 1s, 1p, right? If total is 100, you're going to have half of that going to be s, half of that going to be p. That is 50 and 50, they're going to make 100, right? So 50% is S character if you have SP hybridization. And then if you have SP2, you have total 3 there. You have 2 out of 3 p orbital, and then 1 out of 3 s orbital, right? So if you take 33, so 3 times that is going to be 100, nearly 100. So you're going to have the S33% there. And then if you have the SP3, what is the total you have? 4, right? So 3p and 1s going to be 4. So 4 is total. You have the 1 out of 4 s orbital there, right? So if you take the 100, 25, which is 1 out of 4 of 100, so 25 out of 100 is going to be the s, so 25%. So that's how we're going to call that. This is another way of saying that. The same SP, SP2, SP3. Instead of saying SP hybridization, you can say it's going to have 50% S character, right? Or 50% E character for SP. Alright, so the next thing is the SCDT. So this is also the revision. So we already see this table before, right? So if you have the single bond, so this is single over here, you have the double over there, you have the triple over here. If we compare these three in terms of the acidity, so which one gonna be more acidic? Alkane gonna be the more acidic, right? Correct me.
No.
No, right?
No.
So other way, okay? So you have the arrow over here. So YNE gonna be the more acidic, stronger acidic. So now, for this, you can think from different base. The easier gonna be this. If the acid is stronger, what that means? Acid is proton donor, right? So if the acid gives proton easily in any reaction, that's going to be the stronger acid. If it does not give proton easily, it's going to retain with that. It doesn't want to ionize to give the proton, then it's going to be the weaker acid. Okay? So now you can apply that over here. So here alkane does not want to ionize as easily as the alkyne. So what is the reason? The reason is if it gives proton, it's going to have the electron over here, right? Negative charge on carbon. You're going to have something to make it that stable. If you have, then it's going to favor that. If you don't have anything to make stable for that negative charge there, it doesn't want to lose proton. Okay? So now for the alkyne, you have the charge there, you have the p orbital pi bond, remember resonance, you have the delocalization of electron through the p orbitals, here and there. So that's gonna make more stable. That's gonna stabilize the electron you have there. This is favorable. But you do not have that for the alkane. You don't have the pure p orbital there. All hybrid orbitals, right? So hybrid orbitals are stronger. It's not easy to break or delocalize the electron. You will not have on the sigma bond, but you're gonna have on the pi bond because it is weaker than the sigma one. That's the reason why for the last case, alkyne, this negative charge, once it ionizes, gonna be happy with the p orbitals there. So it can exist easily than you have with the alkane. Okay? That's the reason why the other way you can say that it's gonna ionize. Ionizes to give more H plus ions. If you compare with alkane. That's the reason why it is better proton donor than the alkane. That's the reason why this is stronger acid. Right? That's the reason why in many reactions we're going to see that. We're going to see the ions of that. We're going to see in the reaction later. I'm going to highlight that, okay? So that's what it means. So this point over here, we're going to see the reaction. Alright, so now we're going to go towards the reaction. So one of the reactions going to be making the carbon-carbon new bond. Okay? So you're going to have the two reactant molecules, so you're going to combine them together, and then you're going to make the carbon-carbon new bonds. Okay? So for example, you're going to have the alkyne like this, okay? And then you're going to have the another molecule, so this is just the reagent. It is not saying for that. This is just the reagent, but not the reactant. So something like this. You're going to have, say, alkyl halide. So CH3, CH2, Cl, something like that. Ethyl chloride. Okay. So what you're going to do is you're going to make the new bond with the square carbon. So this carbon over here and this carbon over here. So you're going to connect these two carbon atoms and make a new bond between them, right? So for those scenarios, we can use alkyne. Okay, yeah, it has the use case in that. So for that, you're gonna review what is nucleophile and what is electrophile. So electrophilic carbon and nucleophilic carbon. Right? So remember we defined nucleophile, electrophile before. So do you remember that? It's going to come again and again. Nucleophile is so common that you're going to see this in many chapters in OChem 2 also. So nucleophile is not one single entity, it is the character. Okay? So any molecule, any ion gonna have that character. So you call nucleophile for that. Okay? So you're gonna have many different reagents, many different reactants. They're gonna have one specific character that is nucleophile. Okay? So now here, this one gonna be the nucleophilic carbon, this carbon over here. And then the other gonna be electrophilic carbon, gonna be this carbon. Got a specific character there, right? So, but before that, Nucleophile is any electron-rich center. It can be ion, it can be neutral molecule, doesn't matter what type of molecular ion you have. If that center is electron-rich, so for example, water molecule, right? Very simple. Or ammonia you have, NH3. Very simple example. So it is the neutral molecule, you don't have charge on that, but you have the lone pair. So kind of like you have reserve electron to make bond if needed. Okay? So that's the lone pair. You have two lone pairs on oxygen. So oxygen center is the nucleophilic center. Okay? Sometimes we call for the molecule, it is better to indicate the center that has the electron rich, right? So ammonia, nitrogen is the nucleophilic center. So for the simple molecules, you don't have to indicate that way. You can call the nucleophile, that's simple. But if you have the hydrocarbon like this, so for example, alkyne, now you're going to have the confusion. You have many carbons there. So which is the nucleophilic center? You're going to indicate that. The molecule as a whole is not. So the part in the molecule, the center in the molecule, that has the nucleophilic character. So that center only has the electron excess quantity, but not on the other part. Okay? So now, since it is more acidic, what it's going to do is it's going to give the hydrogen away from there, right? So when it does, what are you going to have there? Minus charge. So that carbon is nucleophilic carbon, we're going to call that, not the other one. So the carbon that has the electron, either a lone pair or ionized electron you have. So that carbon you have the extra electron or non-bonded electron. So that carbon is called nucleophilic center. Okay. So now the other reactant you have, say ethyl chloride, right? So in the solution phase, what it can do is chlorine can take both of the electron with it. It is more electron negative than carbon, right? It can create CH3, CH2, and then you're going to have the plus charge on that carbon, right? So this is the particularly electron deficient carbon. So that carbon is going to be electrophilic carbon. So you're going to call that carbon electrophilic, electron deficient or plus, right? Or if you have the empty orbital without any electron in it, that is the electron deficiency, right? So you're going to call that the electrophilic center. Okay, so now when you have these two, what's going to happen is this carbon has electron, other does not have electron. So now you can make a bond with this electron between these two carbon atoms. And you're going to have the new product. Okay? So this is called the nucleophilic substitution reaction. So we're going to see more examples later. So you can make the new bonding, right? So again, this is the same thing, just elaborated form. So step one, what are you going to have? You're going to have this center created, proton donor, nucleophilic center. Step two, they're going to make a bond with the other one. So that has the positive character over there. So this bond, okay? This is the one we are talking about. So new bond. This is called the nucleophilic substitution in particular. So you're going to call the nucleophilic. So we're gonna have one whole chapter on that. We're gonna see all the details. What are the factors that are gonna make reaction faster, slower, everything in detail. But now, just the reaction. Okay? Yep.
Product HCl on the last slide was the other products. I didn't write this.
You mean over here? Yeah, of course you're gonna have the minor product. So we are dealing only with the major product, okay? So major product gonna have the new bond form. So this is major, right? And then minor, normally you're gonna have the solution in the dissolved phase, right? So what you have in the minor? So this amide ion, this is the dissolved one. So this is gonna be in the solution, right? Part of the minor. And then you have the Cl out from there, Cl minus gonna be in the dissolved form, right? So this one and then this one, NS2Cl, and then you have that H, so H plus gonna be there. So you have H plus, you have Cl minus, you have NH2 minus. So those gonna be in the dissolved form. So part of minor product. That's how you're gonna filter that sometimes, right? So you're gonna crystallize sometimes. So that's how you're gonna isolate the major product, but other gonna be in the dissolved form. Okay. All right. So this is substitution reaction. So now the next gonna be the hydrogenation. This should be easier, right? So hydrogen addition. So this is easier, I mean same as alkene, you're going to do the same thing, but you need to remember one point. So sometimes it can be confusing too. Okay? So if I show you this first reaction, so this is not new, right? So in the previous chapter, you had alkene, you added hydrogen, in presence of metal catalyst, right? Transition metal catalyst. Then you add one hydrogen to one carbon, another to another carbon, and you're gonna have the two carbon hydrogen bond formed, right? So these two gonna be, I'm gonna show over here. So let me show all. So this is hydrogen from the beginning. So the new hydrogen gonna be green color. Okay. So you have the H and H. So H2. So one H is gonna be over here, other H is gonna be over here. So the green H is the hydrogenation. You have the two hydrogen added to alkene. So you have the alkane, right? So double bond to single bond. So that was the reaction we went before, alkene. So now you're gonna have the very similar reaction for alkyne. Why similar? The same type of pi bond is the reactive center over here. So whatever reaction you have with alkene, you're gonna have that reaction with alkyne. Both have pi bonds, right? So you're gonna have the very common reactions. So now, if I add hydrogen like that for alkene, for alkyne, not alkene, right? So now this is alkyne, Y-N-E. So before it was E-N-E. That's the difference. Now you're going to do with the carbon-carbon triple bond. So what's going to be the product? You're going to do the same thing. You're going to break the pi bond and then put the hydrogen in it. So you're going to have the alkane like before. Right? So this is alkane. Do you see any difference here? Alkene and alkyne. Already time's up. So remember this, we're going to discuss more on Friday, okay? So two hydrogen, not one. That's the difference. Okay? Alright.